Okay, how's everyone doing? Bad? No. Oh, okay. All right. Oh, all right. Couple downs, lots of ups, maybe some mediums. Um, very close to Turkey Day, which means that, the week is shorter. Kind of nice. Uh, it's Tuesday, I believe. You're turning in homework 10. You're turning in your check-in, which is cumulative, meaning all of your work. So you're not giving yourself a grade for just the last two things. You're giving yourself a grade for the entire semester, right? Okay.
Can I put the chickens right here?
Thank you. Okay. And then you're giving me a grade, right? I noticed 3 of you have. That's great. Oops. Courses. Oh, God. Oh, God. Which class again? So that's not a passing grade. But if we could get it towards a passing grade, that'd be great. Okay. Okay. All right. So then today we are talking about this type of stuff. Anyone know what we're looking at? Eye of Sauron. Very close, very close. Does that help? Still looks like the Eye of Sauron. Okay. So this we talked about before, how you sometimes have a bright thing in the way. So you like block it out. That's why there's no data in here. It's called a coronagraph. And then you're looking at something that is very dusty. We were talking a little bit last week how you could learn, for example, about the distribution of human beings without having to watch one human being be born, live, and die, just by looking at the different stages. And this is one of the stages in planetary formation. In fact, there's a planet in this picture. This is a debris disk. So planets are forming potentially in there. And there is one already formed planet in this picture. Can you find it? Up left. Oh, yes. This one?
Yeah.
Yeah, okay, that one, that's a good one. Ignore that one, the smaller one. What?
Is it that?
This? No, that's a star. That's the parent star.
Above that?
This? That's a defect in the artifact. Up. Where?
This is going towards the top left.
So this whole thing here, that's like an asteroid belt for this new planetary system. I'll bet you don't get it. What? You have it? Roughly correct. Yeah, it's on the screen for sure. Okay. It's there. Okay. And the cool thing is we can watch it move. So you take an observation, and then 2 years later, you look again, and that little dot moved. Right? So you can find out properties about that object. There's another one here, by the way. Okay. We'll get back to this when we talk more about planetary formation. Does anyone remember what we were talking about at the end of last lecture? I know it was like almost 4 years ago. Momentum, yeah. So we were talking about conserving something called momentum. And then we talked about ballerinas and how they conserve something called we're almost there. Angular momentum, right? Okay. And now we need to talk about conserving energy. And that's not like a money thing going into the winter, right? Conserving energy means that I don't know any way to generate new energy. If I did, I'd have a lot of money, right? So we had this idea here, conservation of energy. We start with the protein bar in the body. That's potential energy. We go up to the top of the hill, and now it's stored in the form of the ability to roll down, and then we roll down, and that is kinetic energy, right? So if you change energy, it has to go somewhere. If you slow something down, you have to use energy to do that. How do your tires slow the car down? Yeah, brakes is the actual mechanism, but what it is that slows it down is friction. And in particular, you know this because if you do a burnout on the street, what happens to the street? Black marks. And those black marks are your tire. Your tire is left on the street. You have to like wear your tires wear down. Even if you don't burn out, your tires wear down because every time that you brake, you're melting off a bit of your tire and leaving it on the street. Okay. And how do you get the energy to start going? Dinosaurs, right? Melted down dinosaurs. Okay. It's actually not dinosaurs, it's grass, but it's not as fun to say. Okay, so energy is never created or lost overall. So as long as you zoom out far enough, it basically all comes from the sun or from radioactivity. So we have a great example here of a person who somehow drank milk and went running. And the energy that they got from drinking the milk came from the cow. And the cow got the energy from the grass, and the grass got the energy from the sun. Right? Yeah. So you're solar powered too. Never thought about it that way, huh? This is an example of friction welding, where we're converting between two types of energy, rotational energy, and then heating. And you can do that so efficiently that you melt steel, right? And people want to do this for capturing waves. You ever seen this before? This is a green energy idea where you have the wave come in, press, and then it like generates electricity for your iPhone or Android, wherever you have. Okay, so we need two of these ideas today. We need angular momentum, the idea that you can conserve angular momentum. And what does that mean again? That means that when an object contracts in size, if it were spinning, it spins faster. That make sense? Should I say that again? I'll say that again. Okay, if you have a large object and you contract in size, if you were spinning, when you contract, you spin faster. Okay. And then the second thing is that energy is conserved. So if I didn't start with a lot of energy, I can't just spontaneously create it. Okay. So let's go back to this idea about how we get the solar system as a whole. How do you form this from a cloud of gas, right? How do you go from this beautiful picture to this beautiful picture? And how does this explain a lot of the properties that we've seen so far? Okay. So we talked about the collapse of the nebula. So you start with all of this gas, really far away, very thin, and then it feels attracted to something in the middle, and it causes it to collapse, right? And once that collapse begins, as you start pulling the stuff closer, then it gets bigger, and so it can pull on more stuff. What is that? What kind of feedback is that an example of? Positive, because it's reinforcing the behavior. You start with some object, and as it pulls in material, it then gets bigger and can pull in more material. So that's a positive feedback for that object, right? Okay. Anyone curious about this part? What causes the collapse? Yeah. Yeah. Gravity will pull it in, but what sets it off? Let's say you start with a big old cloud. What sets off the collapse?
certain chemicals or like components mixing together and then like start something out of nowhere randomly?
That happens much later. So the chemistry gets really important when they get close. Right now, we want to think this gas is really, really far away. That'll get really important when we're close and tight. Yeah. Well, the star hasn't yet begun to form. You start with just a big old cloud. There's no star yet in that cloud. Note the word in that cloud. Yes, something happens nearby. Let's have a look at this picture, okay? Here's this star. What's it doing to the gas? It's pushing it out, right? So if you have some nearby star, for example, pressing gas into other gas, you could start forming stars out here as that part of the gas cloud collapses, right? Or maybe you just have a nearby star that's wandering by and pulls on the edge of the cloud and it starts to collapse. Okay. So these little stellar nurseries, they sort of form near each other. The stars themselves form near in time to each other because one of them forming starts setting off the others. Okay? Okay. So this is the collapse of the stellar nebula, and we're going to break this down in more detail using these ideas that we just talked about. So over here, I don't know why the screen looks so bad, but this is better. You can see the red arrow. So it starts to fall. This material starts falling in towards the center, basically just free falling. And it probably had a little bit of rotation because everything has a little bit of rotation, right? On average. You average everything up, it's kind of turning. But now that big thing collapses down into a little tiny disk and it spins really quickly and it gets super hot. Okay. So why does it spin faster? Gravity will pull it in. What about the concepts we started with at the beginning? There's conservation. We had two things that were conserved. What was the first one? Yeah.
Something big gets pulled in, it speeds up.
Yeah, and what's the example we used on Thursday? Ballerina or ice skater, right? So in this example, the ice skater starts with their arms out. Maybe they're not moving very fast. Then they pull them in and they move faster. Conservation of angular momentum makes us rotate faster. Does that make sense? Why does it heat up? All right, what's that word mean? Kinetic energy. Yeah, so we can think about like kinetic energy would be like the energy associated with motion, right? And so we gave an example when we were talking about gases that like if you're in this room and everyone's sitting down, that is maybe a colder room than if we're all running around, right? And so as molecules bounce off of each other, the more energy they bounce off each other with, the more speed that they individually have, we consider that hotter, right? So this gas is heating up, which means the individual particles are going faster. And the question is, why does it? Okay, so let's look at this picture. This is a really well-drawn picture. I will have no notes on my art. Okay, gas cloud. Not to scale. Okay. But what you're supposed to see is that these little dots are individual pieces of gas. And they're just chilling, they're going this fast. The length of that little arrow and the direction tells you how fast it's going in what direction. Okay? And they're really far away from each other. They're just having a normal life. They're moving slowly. Okay. And then the gas starts to collapse. And they have to move faster because now they're bumping into their friends more. So we start shrinking the size of the room. Everyone gets up to like get out of the way of the walls, right? And then they start bumping into each other. And the more bumping that happens, we perceive as hotter, right? And the way we think about this is a conversion of gravitational energy, the energy associated with this thing being large, into kinetic energy, where kinetic energy is that thermal energy that we just described. Make sense? Could we explain this to our cousins over Thanksgiving? Okay, now this is the hardest one and one that I doubt that anyone will get. Okay, if no one ever does, it's very tricky. Why does it fly into a disk? Yeah, it's the best. Yeah, because like vinyl records, it's the same, right? No, not exactly. Not exactly. Yeah.
Force of this, is always rotating, but then the force of the spin gets so great, it flattens it out as it goes, it gets faster and faster.
I'm not sure I'm following that one. Wait.
So it's all getting condensed in one place, and
Yeah.
it spins faster and faster, and eventually just pulls itself flatter due to the force of it spinning.
Okay.
I'm not sure how to word it.
Can you give me an example? Like, does this happen in life?
Well, spinning a merry-go-round faster out throws you out to the side.
Right.
So
Okay.
it's
Yeah, we saw something like that when we had the rotating carousel, right? So like, does it get flung out? And that's not exactly correct, because in this circumstance, if you were in the disc, you would feel that there was something flinging you outwards, but the attraction is still towards the center, right? And it's a big thing. So it's not getting, if we're getting flung out, it wouldn't necessarily be along the disc direction. You may be thinking to yourself, it's like pizza, spin pizza, it goes into a disc. Is that right? No. No. Discs are not like pizzas. Okay. So these are not the right reasons. Let me just break down why they're not. Gravity is not pulling the material into the disc, even though it looks like it should. Okay. It's pulling everything in spherically. So the flat disk is actually not the preferred direction, right? We don't have planets that are like long pancakes. They want to be potatoes or a different fruit, okay? It's also not like pizza, because individual gas particles are actually orbiting the central object. If you go back to that picture I showed you at the very beginning, each one of those dots that was going around is going around its star exactly like a planet. It's not like sticking to its nearby friend. It doesn't even care about those other objects. Remember we talked about the difference between the Star Wars interpretation of an asteroid belt and the reality? There's a lot of space in between these objects. So for the most part, they really don't know about anything else that's going on around them. For the most part. Okay. So why does it happen? It happens because they run into each other. So as it starts to collapse, there begins a stream of these particles. And ones that are not in the disk more frequently run into those that are in the disk. So what I mean by this, imagine you have a long hallway. It's all filled with students trying to get to class. And you're trying to go from one classroom to another classroom on the other side of the hall. Right? That means you have to cross the street. What are the chances that you get pushed past your class by this throng of people trying to go elsewhere, I don't know, maybe recess? Does that analogy make sense? Okay, so trying to cross through is much harder than simply going with the flow. And that's the reason why you have a disk in the first place. All of this material, there gets some fraction of the disk starts to form, and then everyone else falls in line because it's so much harder to cross through that disk. Good? Okay. Now you understand why it's in a disk. You understand how it formed from a gas cloud. Okay. So the solar nebula spins by conserving angular momentum. It gets hot because of conservation of energy. And the collisions within the disk force common motion. So you're less likely to bump into the person in front of you than you are to bump into someone crossing it. Okay. Well, that explains a lot of stuff that we've seen, right? We're not going to talk about the details of forming a star. That is a class that you can take if you want, Astro 1010. But if you wanted to know why the galaxy also is formed in a disk, now you understand disks. If you wanted to understand why the moons of Jupiter form in a disk, now you understand how disks work, right? It's the same physics over and over. We see this all the time. Here's like a school photo. So all of these kids are different ages. And you can see here, the places where it's dark is the disk. And the reason that it's dark is because it's very good at absorbing dust. Or sorry, the dust is very good at absorbing light. So just like when it's very dusty outside and you can't see very far, that's what's happening here, for example. So the star is right there in the middle. That's the bright light. And then the dark thing around it, you're seeing that disk from the edge. Whereas you might be seeing a different disk here, sort of like edge on, and then you can see the star in the center, and you can see how it's kind of going around. And sometimes they carve out these nice little bubbles, right, of the gas and dust around them. So you can kind of tell their ages based on whether or not they've finished carving their bubble, whether or not they've fully formed this nice disk, or whether they're fully obscured. Like this one here is partially obscured, right? And around all of these are probably planets. On average, we see about 1 planet per star. Cool. That's a disk edge on. So this is a brand new star just forming. And then this is the actual photo of planets being formed. And it looks exactly like Saturn's rings, right? It's got gaps in it and everything. It's got all this material in it. Same type of physics. Okay. So does this explain why all 8 planets in the solar system are roughly in the same plane and go in the same direction? Yeah, right? So they probably all formed like this. They were all heading in the same direction. The reason they're going in the same direction is because if they were going in the opposite direction, they would have crashed into something else, right? Common motion is enforced by collision. You get out of line, we smash into you, you're destroyed, right? So here, let's say I form a little baby Jupiter, and there's a little baby Mars, and there's a little baby Earth. They're all going around like this. And if one of them, like Theia, comes down here, goes the other direction, that's when you smash it. Okay? Okay, good. So if you may remember, we had 4 challenges. We did 1. All right, now we have to explain why there are 2 kinds of planets. You get it? Small, big. There we go. Okay. All right. So what are the 2 types of planets, by the way? Other than the small, big? Rocky bodies versus gas. And which are bigger? Gas. Gas is much bigger. So this is very suspicious, right? Why? It's a conspiracy by the gas. Big gas wants you to have big planet, right? Okay, so how do we build planets? Well, we have stuff. We put that stuff together, and then you make planets. That's fair, right? So what kind of stuff do you need to make planets? Metals? Rocks? Gas? Close. Very close. Ice. You're so close, but we can't have liquids in space because we don't have an atmosphere. Okay. Good, we did it. All right, there's the 4 types. You have helium gas, hydrogen gases. You have hydrogen compounds like ices. And I'm not going to draw a distinction here between like water ice, methane ice, or ammonia ice. Those are all hydrogenated ices, right? Hydrogen compounds, rocks. Just like, I don't know, whatever rocks you read of, who knows? And then metal, whatever that is. Okay. And here we have the temperatures at which they condense. So we've all been doing the homework, so we know what the word condensation means, right? That's when you go from a gas into a solid, right? Because in this particular circumstance, you might say, oh, the condensation that occurs on my cold drink, but that would be gas into liquid. But as we just noted, you can't have liquids in space, okay? You gotta go in from gas into solid. Okay, so if you want to do that with metal, metal actually condenses at a very high temperature. Okay, another way of saying that is that if I take this object and I raise it to 1600 degrees Kelvin, what happens to it? It becomes a liquid state. Yeah, assume this is metal. It's not all metal, but some of it is. Okay, so it goes both ways, right? If I get too hot, I melt. If I cool below 1600, the metal becomes solid. So it is not 1600 degrees in this room, hopefully. And so thankfully, all of the metal is hard and I can see it. Okay, what about rock? Rock is here 500 degrees to about 1300. So there's some more strong rocks, so to speak. They melt at a higher temperature versus the ones that are more easily meltable. And then hydrogen compounds are at about 150 degrees Kelvin. That's where you make your ices. And you can never get hydrogen and helium to condense at all in the conditions that you find it in solar system, early solar system. Okay. Yeah, I said that. Okay, let's see if we can use this information. All right. At 500 degrees Kelvin, and I know you're not supposed to say degrees in Kelvin, but I'm doing it for you. At 500 degrees, what exists in solid form? Is it A, metals, B, rock, C, metals and rock, D, hydrogen compounds, or E, metals, rock, and hydrogen compounds? Okay, final vote in 5, 4, 3, 2, 1. Oh, this is a great question. Really good question. All right, the distribution is like 2/3 for 2 of them, and then like 1/3 the rest. So there's no like clear winner here. So why don't you turn to a friend, ask them what they got. If they got what you got, find a new friend. Introduce yourself. I know it's week 13, but
Yeah. Yeah, I see hydrogen compounds. Hydrogen, yeah. You see, I guess that's. But I think that's the shade, the temperature, it's still like shade. Yeah.
You're ready to revote, just plug it in. Okay, fastest answers seem to have gotten it right. Click in if you.
Some metals for sure. Some.
Okay, let's vote. Final vote. 5, 4, 3, 2, 1. Okay. Someone's really going back and forth between their mind on this. They've clicked on and off like 4 times, 0 and 1. It's not this one. This is too hot for hydrogen compounds because hydrogen compounds melt above 150. Or another way to say that, they condense below 150. I can say it both ways, right? Currently, I'm looking at 500. 500 is above 150. So this would all be melted. Going down here, rock melted. Depends on the rock. Okay, very good. Okay, and what about metal? Metal good. So metal good, rock good, metal and rock good. All right, very good. All right, wait, don't get too comfortable. Don't get too comfortable. I'll rest on your laurels. Okay, ready? It's 100 degrees now. Same question. Okay, final vote in 5, 4, 3, 2, 1. All right. Is it everything? Why not? Yeah, because hydrogen and helium gas can never condense. So it's not E. Okay. So it's now 100 degrees. Can hydrogen compounds condense? Yeah, they can. It's less than 150. So it must be D. Okay. All right, we're nailing them. We're nailing them. All right, let's ask the next question. What the hell does this have to do with anything? Okay. So let's build the planets. So if I get too close to the campfire, it gets hot. If I get far away from the campfire, I am cold. In this analogy, campfire is the sun. I am in the protoplanetary disk, right? I want to be formed. I want to be turned into a nice planet, but not everything is available as a solid or liquid particle. The gas, is gas. So in this region here, you get too close, the only stuff I have is rocks and metal. And once I get cold enough, I pass what we call the frost line, right? The snow line. And now I have ice. And I can build the planet with ice. Okay? Okay. I said that. I said that. So let me, we'll try one more. Oh no, not these many. It's okay. It's very interactive for the next like 30 minutes. Okay, how would the solar system be different if the entire solar nebula had been cooler? With the temperature half of its actual value. A, Jovian planets would have formed closer to the sun. B, Jovian planets would have been further from the sun. And Jovian planets means gas giants, right? Okay. C, there'd be no comets. D, terrestrial planets would be larger. E, Jovian and terrestrial planets would switch places. Everyone got their vote in there? Final votes on 5, 4, 3, 2, 1. Okay. Folks did not like this one. I didn't think that that was credible. It's also really not anything we talked about, so that'd be kind of weird if I just like sprung that on you and that was the right answer. It's not based on anything I just said. What about this one? Terrestrial planets to be larger? Didn't really say anything about that either. Right? We said a little bit about how rocks formed, maybe. Would there be no comets? It's colder, and comets are made of ice. So should ice be more or less abundant? So should there be more comets or less? Oh, okay, so that's definitely wrong. Okay, this one. So now it's just between these, and they look exactly the same, right? No? They look different? Which one is which? All right, we're going to find out because you're split. So today's lecture tutorial is temperature and the formation of the solar system. Okay. Yeah, 3, but not more than 0. And ideally not 1. Just make friends. Number 6. This is 1 for every. No, it's not 1 for every. 1 for every 2 to 3 people. Dang it. Yeah, two sides. You want it to be longer? Oh, okay.
If there's any extras, let me know.
Rodrigo. Axel. Angel. Alex P. Are you Alex? Alex P. There more than Alex P.
Oh, no, I didn't.
Gabriel. Christian. Oh, Ashley. Yeah. Casey. Diana. Regina. Katia. Suryana. I don't know if I'm saying it right. I don't know, maybe not. Christopher. Damien. Yes. Edgar. Audrey. It's definitely not what they said.
This doesn't feel like they saw like.
We can talk about that, but it's definitely not.
That's not a, also not, yeah, that's a little person.
Yes.
So we're just writing now.
Asking for in the back.
Oh, so the range of.
And remember, said. I can like had too much energy. Yeah.
So it's not, but it's so. So water releases it to something else. So. any- Yeah, it's talking. You guys. These ones I got. Let's say.
We should get it.
What grade?
Oh.
So,
I thought it's pretty great to produce guys. I wasn't sure. Yeah, they'll be. I mean, that's your own. Yeah. Yeah, it'd be like, FBI, I used to. Yeah, that's also, yeah, that'd be, gas for sure. That'd be like.
like, that's right.
Finish, don't make sure you, your number. If you finish the, for it.
This here. It was.
Oh, we can switch that. Wait, my bad. You say you're 30? That's really quick, that.
Yeah.
Oh, my bad. Okay, yeah, we said, oh, yeah. Computers forward. Maybe that's what.
So,
Yeah.
okay, so. So. I remember. So. Maybe, yeah. Yeah. Cause if it's cooler, closer, that is so rain, you know, closer in, you can understand. Okay, yeah. There was probably something. I mean, let's really. Like, I don't know, because you got your. Exactly. And so it's not possible. Far away from this.
Okay, how are we doing, folks? Raise your hand if you still need more time. Okay. Revote when you're ready. One of you is still incorrect. Well, of the people who voted. Now many more are also incorrect. People started picking this one and this one. It's going back and forth now. All right, thank you. None of these. 0. Okay, final vote in 5, 4, 3, 2, 1. Okay, so which one of these two is correct? A? I'm just kidding. Okay, so why is that the case? Let's have a look. There is a physical position corresponding to a temperature. Right? That's what the lecture tutorial is talking about. If the sun is colder, that physical position moves towards the sun. Right? Because the whole disk cools down. Smaller fire means you can stand closer to it. Make sense? Okay, we all understood that, Krismani. What the hell are you talking about? Let's go to the next one. Stop it. There's too many. There's so many of these coming up. You're going to be really upset. Okay, astronomers have discovered massive giant planets like Jupiter orbiting at stars closer than 0.7 AU, about the distance of Venus's orbit. Why don't astronomers believe that these gas giants originally formed at that location? Is it A, because the planet's gravity would have been too large to form them that close to the star? B, the temperature in the early solar nebula was too high at those distances? C, the orbital periods are too long for them to be located that close to their companion stars? Or D, a young star's solar wind would have blown the planets further away? Okay, final vote in 5, 4, 3, 2, 1. Okay, most of you got this one right. It is too hot. Okay, good. We're using what we learned. All right, here's another component of what we learned. And that is, what can I build stuff out of? So we talked a little bit about what the disk was made of, the composition of the disk. And most of it is hydrogen and helium. But there's a lot of gas mixed with the dust, right? Mixed with rock and metal. So if I write these ones down, come on now. Oh my God. Classic. Okay. 98% of the gas, all right, 98% of the disk is gas. 1.4% is ice. Rock and metal, only 0.6%. So I'm not a math whiz, but that's at least 2 times the size of this. Right? So that means if you can make a planet out of all 3 of these, you can make it 3 times larger than if you just make it out of this. Now, which of the 2 did we say was bigger? The rocky planets or the gas planets? Gas planets. And guess what? There's more gas. So now we understand why the rocky planets are small. Because there's not a lot of shit. Right? If you have more budget, you can spend more money. You don't have money, you can't buy a big house. Right? That's the low budget house. That's the big budget house. Make sense? Okay. Okay, so that's the next step. So now you start off with a bunch of little tiny pebbles and rocks, and you got to turn them into planets. And that is through accretion. We've said that word a couple of times now, but now we all understand what it means. That's when stuff smacks into each other and sticks instead of colliding into each other and fragmenting. Right? Accretion is to add, fragmentation is to break apart. Okay? So the big get bigger like a snowball, or like the economy, right? And really big stuff that's 10 to 20 times larger than the Earth, get large enough that even though they can't just take gas and dust and make it into ice, they can take that gas and dust and just pull it onto their body with gravity. And this is a really unique concept because instead of, okay, here's the protoplanet, it's a circle, okay, and it's flying through the dust. I'm not gonna throw it, sorry. Okay, all of this material is going through, right? And you collect it on the surface, right? So that would be like running into grains of ice and grains of dust. And you get to keep adding them to your body and making it bigger. Finally, you get large enough that you're gravitationally able to pull gas towards you, so that it falls down and adds to you. So it makes you appear larger gravitationally, and then you can just pull nearby gas. Does that make sense? And you can start at something like 10, 20 and end up at like 100 times larger than the mass of the Earth. Where'd it go? Okay. So objects outside of the frost line, stuff that was able to use hydrogen compounds like water ice, they had more material to build with. So they could start these large cores and then pull that material, right? They had the rock and metal, they pull the hydrogen compounds to make that large body. And then they grab gas around it, right? So here you probably have some form of a core, though this on Jupiter is hotly debated. But you definitely have a core, a rocky molten core in the interior of Saturn, Uranus, and Neptune. And we actually know kind of how big those are. And they get their own little disks, right? So as this thing is going around the sun, they form these little swirling disks. And then in here is where you're going to find things like Io, Europa, Ganymede, and Callisto, right? Okay. Oops. So why is there only 2 types of planets? The first one, what they're made of. Rocky stuff. There's like gassy, icy stuff. Right? And just with the abundance of these objects, like for example, you had a lot less hydrogen. You switched the amount of hydrogen with the amount of rock. You would have massive rocky planets. Okay? So the composition of the disk tells you what kind of objects you're going to find. That's the first part. And the structure, why the rocky objects are in and the icy, gassy stuff is out, has everything to do with temperature. It's too hot interior, so you get small terrestrial planets. Outside of the frost line, you get large gas giants. They start as just rock, metal, and ice cores, They get big enough, they pull gas, and they get bigger and bigger and bigger. A body that is pulling gas to make itself larger is what form of feedback? Positive. Because if I got big enough to pull gas, I'm adding mass to make myself bigger, right? Until you run out of gas. And I'll explain why that happens in a little bit. So did we do it? Yeah, we explained why there's two types of planets. Pretty straightforward. Now, here's the thing, okay? And you're going to see this a lot in this homework. We're getting to a point now where it's not just, oh, is there a crater there, right? Instead, we are building a mental model of how the solar system was formed. And so in order to test that mental model, you are going to see questions like this. Oh, come on. Okay, but you will see them and you will get them on this homework. Okay? And what I want you to be able to do is to think critically about the outcomes. Okay? If I change this part of the composition, if I change the sun's temperature by this, right? What does it change about the solar system as a whole? Okay? All right. See if we can answer this one, and then I'll let you go. Okay. Remember the amount of building material present in the early solar system? It's this fraction, and that's the same thing I just showed earlier, but the only thing is I took metal and rocks and I stuck them into one. Okay. So how would it look if there was a lot of rocks, but only a little bit of ice and the same amount of gas? Would A, there be large rocky planets close to the sun, few small icy planets in the outer solar system? B, gas giant planets with rock metal cores close, and gas giant planets with rock metal icy cores far? C, gas giant planets close, large terrestrial planets far, with the planet composition the same? D, large terrestrial planets close, and small gas planets far? Or E, no different than today? So up here, so this one is 0.6 now, and I'm changing it to 1.9. Cranking it up. You got your final answers in? Final answers in 5, 4, 3, 2, 1. Okay. A majority of you did not get this right. So that's interesting. One group did get it right. That's good. Is it this one? No. So something definitely would change, right? Okay. What about this one? Why not? What's that? Same amount of gas. Okay, so why? I have more rocks. Why can't I have large terrestrial planets close? Oh, I just can't have small gas giants far. Okay, so that one we don't like. Everyone agree?
Yeah.
No one wants to disagree? What about this one? Gas giants close. You don't like this one? Too hot for what? So let's be careful about what we're saying here. Why is it that Jupiter formed at the distance that it formed? Let's go back a step, right? Let's think about what the actual process is here. Here, I claimed that when you get big enough, this big, then you can capture gas. Does this have any argument about temperature? No. So what's the argument about temperature here? What about the water freezing helps this argument? Say that again? Yeah, it makes the base, the core, large because you can add ice. If you can't add ice, you can't be big. Let's go back to composition now, right? This is the one that has all of these different parts. What is more abundant? The rock and metal or the ice? The ice, much more abundant. Okay? That's why as soon as it gets cold enough, you form Jupiter. Right? Because you can build from that material. And then once you've built from that material, then you can grab the gas. So we might have a natural aversion. We might say in our hearts, oh, gas giants can't possibly be made that close. But it depends only on what the composition of the disk was. Yeah. Right. So if I switched all of the mass over to rock, theoretically, I could grab gas. Right? And I could have Jupiter at like Venus. Right? Okay. We're going to go back to that question because many people didn't get it. Okay. I'm not telling you. We're going to do it. We're going to do it on Thursday.